Okay, voltage control with transformers. Transformers can be utilized to control both real power flow and reactive power flow. By controlling reactive power flow, you can control the voltage on one side of transformer, because based on this formula, we know if we increase voltage on one side, that will affect the reactive power flow. To control real power flow, we need to control the angle, because the real power flow is approximately proportional to the angle difference. So there are two types of transformers which can help control the real or reactive power flows. Basically, they can help control voltage, because voltage include both magnitude and also phase angle. So at the end of the lecture on Friday, we talk about the type changing transformer. Type changing transformer, you just move up. There's a tap position, so that will change the ratio of turns of primary and secondary winding. So usually the range can be up to a positive and negative 10% of the original voltage. This lecture, we are going to talk about the regulating transformers. The regulating transformer can change the voltage magnitude and phase angle, such as it can help control both active and reactive, real and reactive power flow. Okay, to control voltage and magnitude, it can add a voltage proportional to the voltage of one phase, or between maybe the line and the neutral point. That voltage is induced by itself. By itself, which means it will add a voltage phasor to the original voltage phasor. So that added voltage phasor can be positive or negative depending on direction, so which can cause increasing or decreasing the original voltage. So that's the idea. If we use the regulating transformers for voltage magnitude control. You can also select a voltage which is different from original voltage, because think about it, we have three phases. There are three phasors separated by 120 degrees. You can choose phase B to induce one voltage added to phase A. So that will influence the phase direction a little bit for phase A. Okay. You can also pick maybe voltage orthogonal to original phase, which is showing here. Which will give you better control of the phase angle. So this is one design for voltage magnitude control by using a regulating transformer. So regulating transformer has two components, basically has two transformers. The first is called exciting transformer, that just to take voltage from the original phase. Then it will give that voltage into this series transformer. The series transformer will influence the voltage on the lines. So if those two are equal, that will add this voltage to the original phase. If that's opposite, that will cancel the original voltage a little bit. So we'll either increase or decrease. So depend on this switch. So this switch, if it's right now, is at the position number 2. So there are two positions. So if it's at position number 2, so that will take the voltage here, right? So because it will utilize this winding, this secondary winding, to get a little voltage proportional to the original voltage on one phase, phase A, but in the opposite direction. So give that voltage should be should give that voltage to the transmission line and cancel the original voltage. So if we move up to tap position number 1, so it will induce voltage in the same direction. So by changing between the position 1 and 2, so you can decide to add either increase voltage or decrease voltage. So you can keep the series transformers here to control phase A, but for the exciting transformer, you can move to connect the primary side to a different phase. It can be phase B, phase C, or for this design, it try to get the voltage between B and C. So by still using this design, so you can switch between 1 and 2. So that will add a little voltage to phase A, but this little voltage is proportional to voltage between B and C. So why do we need to use the VBC? Because from the phasor diagram, so this is phase A, phase B, and phase C. So to get the voltage between B and C will be a phasor, because we calculate VBC is equal to just VBN minus VCN, right? Which is equal to drawing a phasor starting from the head of C down to the head of B. So basically, which is exactly this one. So that one is orthogonal to VAN. So if you want to change the phase, not the magnitude, so using orthogonal will be very effective. So depending on the ratio here, so you can decide the ratio. Even the ratio can be adjustable. So you will generate a little voltage in the same direction of the VAB, and by this rectangle, so you will change both magnitude and angle, but basically the angle is dominant purpose here. So you will generate a new voltage. So that will be the new voltage on the receiving end. So that will have an angle shaped by alpha. So why do we want to change the alpha? Because based on this formula, real power flow depend on the angle difference. So if you change the angle difference, that will change the real power flow. So this picture gave you one example from a real system. So assume we want to deliver 530 megawatt real power from one substation to another substation, but there are two transmission paths. The first one is overhead line. The second is underground cable. They may have different lengths or different material, but after we finish this section, we move to the next section about the line perimeter. So I'll explain why underground cable will have smaller reactance compared to overhead line, even for the same lines. Because underground cable is installed under the ground, it will have more capacitance, which can somehow cancel some of the reactance. So that will make, if it's underground cable, which is equivalent to reducing this reactance. So if this is reduced, even with so that will increase the real power. So even you send 530 megawatt from location 1 to location B, because there are two paths. The first one, overhead line, only delivers 90 megawatt. The underground cable delivers 440 megawatt. So that's not very efficient, because we're not fully utilizing the capacity of the overhead line. So for this case, that's a perfect application of phase shifting transformer as part of the regulating transformers. So what we need is we add a phase shifting transformer at one substation, which is connected in series with the underground cable. So that phase shifting transformer only need to change the angle by creating a 3.5 degree phase shifting. So that will reduce the angle difference on underground cable. So from these formulas, so by reducing this angle, so you can reduce this power flow. So eventually the real flow of the overhead line will be roughly same as the flow of the underground cable. So that's application of a phase shifting transformer. Okay, so that's the last thing I want to say about transformer. So next we're ready to move to the next idea, which is the per unit system. Because we introduced the modeling of transformers, and transformer will split the transmission network into many sections of different voltages. So think about you have a generator, which generate electricity, usually not very high voltage, at maybe 35 kV, usually lower than 50 kV. Because you don't want the installation cost with generator to be too high. But once you generate electricity, in order to improve the efficiency, you want to raise the voltage to very high, like 500 kV or 345 kV, to deliver over the backbone transmission network. But to utilize electricity, you have to decrease voltage to sub-transmission level under 100 kV, then give the electricity to a distribution system. So there are many voltage sections. So to do the calculation for such a power network with many different voltages, that can be very, very complicated. So that's a strong reason to introduce the per unit system. A per unit system is just for any quantity in the power system. Basically, per unit means no unit. So why does it not have unit? Because we define base value. So base value is like the value usually they should operate. It can be a rated value, it can be nominal value. And the actual value will be divided by base value. So such as the per unit value will basically like a percentage or fraction of the base value. So that's why it has no unit. Definitely after you finish calculation, you still need to multiply the per unit value by base value, then to get the actual quantity. But that's only the last step. So before last step, you'll be fine to use the per unit value through the entire calculation. By using per unit values, we can neglect different voltage level transformers, lines, and generators. And we can use per unit value for power, voltage, current, impedance. They all have very different units. Give you one example. So let's say this is a simple power system with one generator operated at 22 kV using a step-up transformer. So I will want to deliver the electricity at 345 kV system. So the entire high voltage network. So basically this system has 3 sections, right? This is separated by transformers: section 1, section 2, and the section 3. Right. So we have 22 kV system, 345 kV system, and so this one is roughly like a 140 kV system. Or 143, so roughly at that voltage level. So we have 3 different voltage level. So do such calculation considering even for voltage, we have they're using the same unit at volt, but they have very different voltage at different sections. So that's not convenient. Also, a drawback of using the actual unit is we don't really know which end has higher voltage, which end has lower voltage, because it seems to be those numbers very, very large compared to a 143 or 22, but we don't really know how high they compare to their nominal value. Okay, so if we divide each number by their nominal value, rated value, base value, so we will get percentage of voltage everywhere. If the system is operating completely in normal condition, everywhere the voltage should be around 100%. Otherwise, there will be cause some violation and reliability issue. So we just choose 20 kV, for instance, 345 and 130 kV as the base voltages. We just assume those 3 numbers are their nominal voltages. Okay, so next thing, we just divide each actual voltage by the base value. So you see if the generator operates at 1.1 per unit. So which means if 20 kV is there, it's really nominal voltage. This generator right now is operated slightly higher than nominal voltage by 10%, which may not be bad. So the generator has this capability to control the voltage. After transformer, this substation will have about 4 to 5% higher than nominal value. And after delivering active and ready power, so the other end will have slightly lower voltage, 3.8%. Then to this bus, that's basically the same voltage at nominal value. Also going to this direction, so you see how much voltage you have. And so for this case, you see this voltage is higher than the nominal value by 3.6%, and this is 3.2%. So probably the bottom transformer, even a step-down transformer, which means is sending power from a high voltage system to low voltage system, but receiving end may have some voltage control to slightly increase voltage relative to the base value. So this is a much clearer picture to see where you may have high voltage problem, low voltage problem. Another example of this application is from a project I did back to 2010 for Electric Power Research Institute. So you may have recognized this is basically Tennessee. Yeah, this project was done for TVA. So in 2009 or 2010, we demonstrate one applications which can collect phasors at many different locations of TVA substations. All the data is actually synchronized by GPS. So such equipment is called single phasors or phasor memory unit. At that time, such units have not been were not very popular, but right now that become basically industry standard. You need to have such device everywhere. But at that time, we want to demonstrate the power of synchronizing all the measurement using time signal. Such as you can see a really big picture about the entire Tennessee power network. So you understand the network has many different voltages separated by a transformer, but we use per unit value. So you see every number, so those numbers just indicate the voltage in per unit. So most number is around 1. So for example, this 1.0, this is 1.04, and 1.06. So by looking at those data, we understand the voltage pretty close to their nominal value. So even their actual voltage level can be very different. So you can quickly recognize some area you have slightly higher voltage, some area have slightly lower voltage. So it's very convenient using per unit values. So now let's talk about the definition and also calculation of the per unit values. So in this entire course, and most of our efforts are dealing with 4 types of quantities: power, voltage, current, and impedance. All right. So if you want to calculate per unit value of all 4 quantities, we have to have 4 different base quantities, right? In power, maybe yes, because it complex power, so may not be a real power, so it can be VA. So basic unit is VA or MVA. So voltage will be volt, and current will be ampere, and this impedance will be ohm. Basically, there are 4 different units. So we need to define 4 different base quantities, and then for each actual value divided by the base quantities, so we can have per unit power, per unit current, per unit impedance. So we need 4 base quantities, okay? And all the base quantities are real because we understand those voltage, current, impedance, they also have angle. They are either phasors or complex number with angle, but we don't define which angle to be standard. So we just make all the quantity to be real. So they are not complex numbers. So even we just still take the naming conventions of power, but phasors, but they are not complex numbers. They're real. Such as the per unit value will have the same angle from the original value. But actually, because we know the impedance is equal to voltage divided by current, so which means VIZ, they're actually independent. They're independent each other, right? And also power is equal to voltage multiplied by current. In 3-phase system, you also need to multiply by root of 3, but they're also dependent. So which means we don't have to define 4 independent bases. We just define any 2 of them. Okay, so the other two will be calculated. So in practice, usually power and voltage are often given. Why? Because each device, if you check the plate, they have the rated power. Okay, so we just take that rated power as base value. Oh, maybe we define base value according to that rated power. So that's pretty natural. So it doesn't matter the equipment is single phase equipment or three phase equipment. We always use the power, the total power at the base for that equipment. And the voltage is also very obvious. So because some equipment, they can operate at full capacity, at high current or low current, but the voltage usually should stay about the same. Okay, so but which type of base value do we need to select? Because we are talking about three-phase system. Usually for power, we pick three-phase base volt ampere, basic apparent power of three-phase. Usually the unit will be MVA because most of the device will be at the mag power level. For voltage, we pick line-to-line voltage, not the line-to-neutral voltage, because some devices, they don't have neutral line. So it's not convenient to measure the actual voltage between one line and the neutral. There's no such point. Even you measure between the ground, that doesn't give you the accurate line-to-neutral voltage for most of conditions. So the most convenient way is just measure line-to-line voltage. So usually it's at a kV, kilovolt. And current, we just use line current of single line. If the device is Y-connected device, so that is also the phase current. Impedance, we pick a line to neutral impedance to calculate the base, to define the base. All right, so we'll have some useful formula. First, if we know the base for voltage and current and power, base will be the product multiplied by the root of 3. So because it's a three-phase system, line-to-line current, line-to-line voltage divided by root of 3 will give you a line-to-neutral voltage. Line current basically the same. Line current, if you already know the power, the three-phase power and the line-to-line voltage, so this will give you the line base value. And finally, impedance can be obtained by knowing this one. This is a line to neutral voltage. Line to neutral voltage divided by line current, so that will give you the line to neutral impedance. Or you can use this formula. Okay, so all right, let's talk about how to calculate the per unit quantity. So with base value defined. So from previous slides, those formula are very useful for us to find the base value from already known base value. Basically, calculate the base value of current or impedance from voltage and power. One good thing of using per unit value is, so it doesn't matter you're studying a three-phase system or one-phase system. So in the equations on per unit value, you won't be able to see such a 3 or root of 3 factor. So that can be a very annoying if you use the physical value, but now they're completely gone. Yeah, basically, if you do the calculation using per unit, we go back to the original formula in single phase system. Don't worry about which formula you need to have such a 3 or root of 3 factor, which don't. Let's prove why in per unit system those factors will disappear. So here I just gave you a Y connection as an example. So you can definitely try delta connection. So they could give you the exactly same formula. So Y connection, okay, so we want to prove the first formula, the V per unit will be the actual line-to-line voltage divided by line-to-line base. Line-to-line voltage is 3, this factor, the root of 3, times line-to-neutral voltage divided by line-to-line base. Okay, the line-to-line base divided, then we move this factor down. So which will be here. So that make the denominator be the line-to-line voltage divided by root of 3. So immediately, so the phase voltage is equal to the phase impedance multiplied by phase current. And this denominator basically is just the base for one phase, so which is equal to the product of the impedance and the current for the base value. All right. So next you just, for the last item, immediately you get per unit impedance and per unit current. So that's done. That proved this formula will be always true in three-phase system. You just need to make sure when you calculate per unit value, you use line-to-line voltage at the base value, three-phase power at the power value, base value, and the line current as the base value, and the line to neutral impedance as the base value. So if you define those four and then calculate the per unit value, you define they have to be those four base values. Then those formula will be correct. So next is the other two expressions just prove the second and third equation also true. I don't go into the detail, but you can very quickly recognize how each one is proved. You can definitely try to prove the three formula for delta connection. So anyway, so in per unit formulas, we won't be able to see such factors. It's similar to calculating for a single phase system. Okay, so next we want to talk about the change of the base. So as I said, the base can be the rated value for this equipment. For example, I have a equipment, the rated power is 1 megawatt. So maybe I need to use a 1 megawatt at the power base, and the equipment is operated at maybe 15 kV. Then the 15 kV will be the voltage base for the line-to-line voltage. But if I have many different equipment, sometimes I may want to define a common base. The common base, which means it doesn't it doesn't match exactly the rated value of the equipment, but it's just for convenience. We don't want to deal with so many bases. So let's just define the power base to be a 10 megawatt, which is 10 times of the rated power of this equipment. But I need to keep in mind, if my calculation tell the power in per unit is 0.1, which means that's already the full capacity, because I change the base. Okay, so there will be some cases we need to change the base. So assume we have a power base, we call it old base, an old voltage base. Okay, so this formula is from here. Old per unit value multiplied by the old base, it will give you the actual value. So this one doesn't change. Yeah, this one reflects the actual impedance of the system. That one doesn't change with the base. You can also calculate the per unit value based on a different base, a different power base, different voltage base. So it gives you different impedance base and different per unit value. So those two can be different, okay? But the actual value has to be same. Yeah, that doesn't change. All right, so this case tells us we can select any base value. We don't have to make a base value to be exactly at their rated value or some value they typically use. We can, for any to serve some purpose, we can choose a different voltage or different power value at the base. So that will give us the different per unit value, but that doesn't affect the actual physical value. So we can utilize this equation to derive a useful formula to convert from one per unit value to another per unit value of different base. So that will be this formula. Okay, So if you know the old base value, a new base value, plug into this formula, so you will transform old per unit value to new per unit value. So if you have chance to take look at any transformer generator nameplate, so nameplate usually will show the power, the rated power, the rated voltage, which are very important. And sometimes they also give you a impedance, which is some number with unit percentage, like 20% or 10%. So what does that mean? So that actually means the per unit impedance of rated value, using rated value as the base values to calculate the per unit. So if you see 20% for impedance, that means if you use rated power, rated voltage at the base value, that per unit impedance will be 0.20 per unit. So that's exactly the same thing. Okay, but that nameplate is based on assumption of only the rated voltage, rated power are used as the base value. But when you connect such devices into a network, sometimes a system prefers single common power base. Yeah, that's very convenient. And that common base can be bigger than the capacity of some equipment or smaller than some other equipment. But it doesn't matter, but it will be more convenient to the calculation. So then we'll need to use this formula to convert that X percentage to the correct per unit value. So then the formula will become, if we know the rated value, and we also know the system base, system voltage base, and system power base, using this formula will change from the rated impedance per unit value to the system base per unit value, right? So in this case, this one will be the X percent on the nameplate. And this one will be the one we're going to use for calculation. And if the device had the system-based voltage and is equal to the equipment-based voltage, the rated value, which means this parenthesis will be 1. This one doesn't change. Then that will simplify the formula. Only just need to use this one to change the impedance base, to change the per unit value for impedance, and the per unit value for voltage, they don't change. Okay. Here is one example from the actual model of a power system in the US. That's a standard data format of the network or power flow data. So you see this first column is just the location number, and this is location name. And this column indicates at 500, 345, those are just the voltage level. Those are their just rated voltage. Of those numbers, you see some negative, some positive. That should be power, either injection or either load or injection. And this column, you see there's a lot of number, very close to 1. So this number 0.98437, right? So if you check the number, very close to 1, that is actually per unit voltage value. And those number, so the number usually change around between maybe 0 to 40. So usually that's angle. That's angle. So that's degree. Okay, so this is standard data sheet. So it gave you the voltage base based on the rated voltage, and this number here, 100. This is 100 MVA. This is the new system common base. So you can put any number there. You can put this number 200. The entire system will take this, the new power base. And in this case, we know if we don't change those values, we take the same, the rated voltage at the base, we'll only need to use this formula to recalculate the per unit. So later, I'm not showing the entire data sheet, but actually there's a later section showing the per unit value. So we need to use this formula to update the original per unit value to the new per unit value. Like for instance, right now, if the system base is become 100, if the original equipment base is 500, so you actually need to divide the original per unit value by 5 to give you the new base value, new per unit value. We'll come back to a similar example in the project number 2. Because in the project number 2, I will give you some data similar to this one. So you'll decide whether we need to update those per unit value. Okay. So what are the advantages of using the per unit system? All circuit laws are still valid in the per unit system. Okay, even their unit become no unit, like per unit, not actual unit. But they gave a very clear idea of relative magnitudes of all quantities such as current, voltage, power, and impedance. The impedance is in ohm with the same type of equipment vary greatly with the rating, but their per unit impedance is falling to the very narrow range, regardless of the rating. So when you do the project 2, you'll get idea on what this sentence means. Because when you look at the data for the transmission line about the similar voltage level, their per unit value or similar type of transmission line, the per unit value are pretty close in the same range. This is very important for developing any software program to do simulation, right? Because if you solve some equation, if you develop the computer program to solve the power flow, do simulation for the grid, you want to, when you allocate the memory, right, to deal with the impedance line current, you want the value to be staying in the same range. You don't want to see this impedance is like 1,000, that impedance is like 10 to the power -7, right? So you have to determine the smallest number, the largest number to allocate the memory, determine how many beats you want to save this number. But if all the values stay in very narrow range from 0 to 1, that's very convenient for the programming. For transformer, the per unit value of impedance, voltage, current, all the same, regardless of whether they're referred to the primary or secondary side. So that's also a very good thing. You may already see that from this example. So this transformer, once we have the per unit value, those transformers seem not existing at all. Okay. It will become something similar to transmission line. We still need to calculate the impedance or the readings of transformer in per unit. So transformer itself become maybe can be approximated by just the reading. And if we go back to these slides, we don't worry about whether we transfer everything to the primary side or secondary side, because you see the equation have a completely same structure. When you translate all the voltage, current, impedances to the per unit value, they are same, exactly same per unit value. Okay. So for three-phase system, we don't have those factors, right? Those very annoying factor, and this is ideal for computer programming. So the last 2 minutes of this lecture will go through. There's 2 examples, very good example on the textbook. So we may have some homework problems similar to those examples, and also I will give you the midterm exam problem similar to the examples. So starting from now, we will deal with some power network. Okay, we have a generator, we have load, we have transmission lines, we have transformers, and we'll talk about how to do the calculation. Okay, so although we have not been able to solve the like active power flow or do any control, but we can start do some calculation for power network. Okay, so here you see there's a generator powering the load and also a motor. So G means a generator and I means another motor. And also you see this symbol that indicate the load, maybe some other load. There are two transmission paths. One pass at 220 kV, the other is at 110 kV. The generator operates at a lower voltage. So those are the summary of the nameplates from all the equipment. So generator operated at 22 kV. So I need to have this step up transformer to change from a 22 right, to 220 kV and deliver through this transformer. The motor is operated at 10.45 kV. So you need another transformer to decrease the voltage. And the second transmission path is at 110 kV. So you need to change it to 110 kV from 22 kV. Similarly, here you also need to go back to this lower voltage. And each equipment has the power, which is the rated power. And it has the voltage, rated voltage. Okay, so we can use the rated voltage as the base values for calculation. But the power will depend on the requirement. So for this specific example, it asks you to take a common base, which is 100 MVA at the base. So for every equipment, you need to use 100 at the base value. So even the nameplate gave you some rated power, so you may want to change the base for the new per unit value. So on the nameplate, they give you those X value in percentage. So those are the per unit value calculated using, if you use exactly this column as power, this column as voltage, so you will have this per unit value. But right now we want to change the power base. And the question also specifically asks you to use 22 kV on the generator side as a base value of generator. So this is 22 kV. So that's the same as the rated voltage, so which is good. So for the generator or also the transformer connected generator, we don't have to change the voltage base. We only need to change the power base. Okay, so let's define those notations, VB1, VB2 to VB4, and VB6 just define different voltage base value. Okay, so VB1 is for generator, and the VB2, VB3 are mainly for the substation number 2 and the substation number 3. But because they're connected by the same transmission line at the same voltage, so we know the VB2 is basically same as VB3. For substation number 5 and 6, if they have the voltage base value, they also equal. For motor, there will be another base value, VB4. Also, we need to calculate the number of the impedance base. So for the line, we need to know the line impedance, first line impedance, the second line impedance base. And for the load, we also need to calculate the load impedance base. So we have a number of things to calculate. First, let's find the base voltages through transformers, because transformer define the ratio. So if we know the VB1 as 22 kV, by using this transformer, we actually also know VB2 and the VB3, right? From VB3 through this transformer, we can also calculate VB4. Similarly, we can do for the second transmission path. The second part, we need to change the equipment base from their original base value to the new base value, 100 MVA. Okay. So for each transformer, the base value still need to meet this equation. So the ratio of voltage bases will be the ratio of the number of turns. So if we know one base, original base, by using the ratio, we can calculate the base of the other side. So that exactly calculating from this 22 kV to get the voltage on the other side, which is like 220 kV. Okay, so that's pretty straightforward. For substation number 2 and number 3, the voltage base will be just 220. It doesn't change at all. For substation 5 and 6, it basically just 110 kV, the same as that line voltage. For the motor, that is 11 kV. This one is not known yet, because from here we have a 220 kV, and from the ratio, this side will be 11 kV. So this side will be 11 kV. Okay. So next we want to change the equipment base. We'll start from this formula. Okay. So here we just plug in the rated value and the common system base. So for generator, the voltage doesn't change, right? We only just need to use the power to update the per unit value. So you see the per unit become 0.18. It doesn't change. 0.18. Original 0.818 will change to 0.2. So this 0.1 is from 18% of the nameplate. So now it becomes 0.2, become 20% based on the new base. Similarly, we can update the per unit value for the other equipment. So you see they all change based on the original rating, power rating, and the new common power base. For the motor on the plate, it said they operate at 10.45 kV. But in the network, we need to make sure the power base of the motor side also meet the ratio for the transformer. So that will also need to update the transformer per unit value. Okay. So next we just can calculate the impedance base value for both lines and the load. Then we can calculate the per unit value for the line and load. Okay, so I don't go through this last example. You can read the textbook. I basically just use the calculation from previous example to draw this circuit only based on per unit value. So using this per unit value, they ask you to calculate voltage, 3 voltages. Okay, it's very straightforward because there's no unit anymore, and it doesn't show transformer. So it's just like calculating for a circuit. Okay. It gave you the voltage at bus 4. That's what the example gave you. Also gave you the power, so you can calculate the current, and from this current, and you can calculate also this current, and then you can get the total current. So it's pretty straightforward, like a circuit calculation. This step is just to calculate the total parallel readings. So using that readings, you can calculate this voltage and motor voltage and substation 1 voltage. Yeah, I don't go to the details. You can easily understand those steps from the textbook. All right. So on Wednesday, we're going to have a quiz for this session. I will make a starting time maybe around 8 o'clock until 4 or 5 o'clock in the afternoon. And we'll start the next session about line parameters. All right, thank you.
Is the quiz just over concepts or is it actual calculation?
No calculation. It's just true and false questions.
Okay.
You're not this. You're
I want better.
Good morning, breakfast. Come on, cheers.
Sorry, dude.
I probably show it.
You're gonna be in the library later.
Give me my cane. I know my stuff. No. Negative.